Okay, so this presentation is the second part of our previous discussion and conservation of energy. Okay, so in our previous discussion, all the types of energies included in the system for conservation of energy are now discussed. Okay, so by this time, we are now going to consider the steady flow energy equation, okay, or SFEE. So this is the second corollary of the first law of conservation of energy. Okay, so the principle applied to open system. So and therefore, the mass and energy crossing the system's thermodynamics boundary are considered constant. Okay, so mass as the mass crosses the thermodynamic boundary, it doesn't change. Okay, so considering the illustration below the slide, so we will notice that the previous energy discussed in the first part of the topic so is now present in the system. So like say for example, the potential energy at 1 here. Okay? So at point 1, kinetic energy, the flow work or the flow energy, internal energy and enthalpy. And take note that Q is also included. Okay? Same as for at point 2. There is also a potential energy at point 2. Kinetic energy at 2, flow work at 2, internal energy at 2, and the enthalpy at 2. So take note that in the law of conservation of energy, there is no degradation of energy. But the energies involved are only changed into another form of energy. Okay, so take note that the system also involved work. So take note that the consideration of heat and work here are positive. So take note, if Q is toward the system or heat is toward the system, heat is positive. And if work is coming from the system, the work is considered positive. Okay? So, let us now proceed to the equation. So, let us take an energy balance from the previous illustration. Okay? So, energy entering is equal to energy leaving. So, what are those energy entering the system and what are those energy leaving? Okay? So, entering is potential energy 1, kinetic energy 1, workflow at 1, internal energy at 1, enthalpy at 1, Q is equals to potential energy at 2, kinetic energy at 2, flow work at 2, plus internal energy at 2, plus enthalpy 2, plus work. Okay? So, take note that this is now the general equation for steady flow. Okay? So, let us now consider again the units of energy. So, take note, in our previous discussion, in part 1, we already discussed. Okay, so let us again analyze, okay, the units of the energy involved in this topic. Okay, so again, Q is equals to MCP delta T. So this is for open system. Okay, so Cp is equals to 1 BTU per pound degree Franklin. Okay? This is the same as with 1 BTU per pound mass of water degree Fahrenheit. Okay? So that is British thermal unit. So we know that a British thermal unit, it is the amount of heat required to raise the temperature of 1 pound of water through 1 degree Fahrenheit. Or the change in degree Fahrenheit of 1 is the same as with the change in degree Franklin. Okay? So take note that the water is at 14.7 psi at atmospheric pressure. Okay? Okay, another is kilocalorie. So what is kilocalorie? So this is in MKS. Okay? So kilocalorie is the amount of heat required to raise the temperature of 1 kilogram of water through 1 degree Celsius or 1 degree Kelvin. So take note that the change in temperature in Celsius is the same as with the change in temperature in Kelvin. Okay? So take note that the atmospheric pressure is equivalent to 1.03 kilogram per centimeter square. Same as with 14.7 psi in English, and that is also 101.325 in SI. Okay? So therefore, the specific heat now of water is equivalent to 1 kilocalories per kilogram Kelvin. Okay? So again, kilojoule. So kilojoule is the amount of heat required to raise the temperature of 0.2388 kilogram mass of water through 1 degree Celsius or 1 Kelvin at 101.325 kilopascal, or simply the equivalent is 4.187 kilojoules per kilogram Kelvin. Okay? So that is now the value of specific heat at different standards. Okay? So let us take this example. Okay? A centrifugal pump compresses 3,000 liters per minute of water from 98 kilopascal to 300 kilopascal. Okay? The inlet and outlet temperature are 250 degrees. Okay? So the inlet and discharge piping are on the same level. So there is no such change in potential energy here. So because the inlet and outlet is at or are at the same level. So but the diameter of the inlet piping is 15 centimeter, whereas that of the discharge piping is 10 centimeter. Determine the pump work in kilowatts. Okay? So take note again, energy entering are the same as with the energy, or it's the same as with the energy leaving. Okay? So take note, bringing down the energies involved from the original equation. Okay? So writing now up here, and then eliminating those energies which are not present, and then the remaining energy involved is equal to kinetic energy, flow work, and then work. So potential energy is eliminated, internal energy is also eliminated, so there is no change in temperature between the system, between the two state points rather. Okay, there is no enthalpy involved. Okay, and there is no heat transferred from the system. Okay, So, kinetic energy now plus flow work at 1 is equals to kinetic energy at 2. Flow work at 2 plus work. So, by this time, we are now going to determine the work. So, by transposing those parameter to the left, we now get. Okay. So, but before that, let us first determine the velocities at the inlet and the discharge since kinetic energy is involved. Okay? So, from continuity equation, Q1 is equals to Q2. Okay? So, where Q1 is equals to area or the cross-sectional area at 1 at the inlet rather. Okay? Multiplied by the inlet velocity is also equal to the cross-sectional area at 2 and the velocity at 2. So, take note that the discharge is 3,000 liter per minute. Okay? So, substituting the values and then the velocity now at 1 is equals to 2.83 meter per second and at point 2, 6.37 meter per seconds. Okay? So, again, the equation kinetic energy at 1 plus flow work at 1 is equals to kinetic energy at 2 plus flow work at 2 plus W. Okay? Substituting values, kinetic energy at 1 equals to 1 half mv square. Okay? So, substituting values, the value now of W is negative 10.91 kilowatts. Okay? So, I think it is clear. Okay? Next example. An air compressor compresses air with enthalpy of 96.5 kilojoules per kilogram to a pressure and temperature that have an enthalpy of 175 kilojoules per kilogram. So there are 35 kilojoules per kilogram of heat lost from the compressor as the air passes through it. Okay? So neglecting kinetic energy and potential energies, determine the power required for an air mass flow of 0.4 kilogram per seconds. Okay? So this is very easy. Okay, so using now the original equation for steady flow energy and then eliminating those energies which are not involved. Okay, the remaining energies of course is or are enthalpy, heat added, and then the final enthalpy and the work. Okay, so substituting values now for enthalpy, the mass multiplied by the enthalpy, and then mass multiplied by the heat transferred plus h sub 2 175 times 0.4 plus W, where W now is equals to negative 454. So why is it negative? So because the system is a compressor wherein W is done to the system. Okay? Thank you very much. Okay? So that's all.